what were the kinds of performance engineering choices that made that 10 to 20x cost reduction possible?
Yeah, and what's really interesting, of course, is that due to the Chinese export, restrictions, U.S. export to, China, um, China, in theory, cannot get a hold of the best chips, so they had to find clever solutions. One that stands out is they found essentially a undocumented or an underdocumented. I would say all of NVIDIA stuff is really underdocumented. So, but they found one in particular way to bypass a particular cache or short circuit. I would say just keeping it at a high level, which led to huge performance gains in this sort of limited capacity chip. And it's something someone asked the OpenAI folks if they have discovered the same thing, and Sam Altman and company said that they're positive that DeepSeek, or that they being OpenAI, has found all of the same tricks that DeepSeek has found, without getting into details. So these things aren't necessarily that sort of revolutionary. It's just no one talks about them. The labs have them as their secret sauce, and it just so happens that DeepSeek was open source, and they talked about this. A lot of other innovations, though. I mean, DeepSeek had what was called the Open Source Week that I mentioned in the first chapter, and really it was not just sort of CUDA type innovations, hardware innovations, but it was co-designing, which is the term that is starting to be used quite a bit. They figured out ways that they can modify algorithms, they can modify, the actual software, and they can tune it specifically for their set of hardware. Also included in that hardware is the storage system. So they actually wrote their own storage layer, which is very interesting. This is something Jensen has just started talking about more and more. I think it was last year's GTC, where is the first time that you really hear Jensen and the NVIDIA folks talking about the storage layer, that storage layer being extremely critical, because it is a bottleneck. Basically, picturing all the different bottlenecks, memory access, and compute is basically we on a single machine or a single cluster, we've got a lot of compute. It's just all the other bottlenecks, right? Which is like retrieving data from memory from storage. Yep.
Right. Yeah. So Jensen, of course, Jensen Huang, the CEO of NVIDIA, probably all of our listeners already know that, but filling in one tiny little blank there. And going a little bit more into that DeepSeek paper and DeepSeek R1 release, they treated communication bandwidth. It's kind of, you were implying it there, but communication bandwidth as the scarce resource. So for a developer today, an AI engineer today, who feels that they're compute poor, but maybe they actually aren't, maybe they're bandwidth poor, how can they fix that? How can they optimize that on their GPU instead of just buying more GPU hours?
Yeah. The most critical metric or characteristic of a GPU system these days is the memory bandwidth, right? So a lot of times people focus on flops and teraflops and tensor cores and quantization, without getting into too much detail there. You really want to look at from generation to generation, pay attention to the memory bandwidth. How fast can I get the weights, of these 500 billion parameter models, 1 trillion parameter models? I need to load those into the GPU, into those registers, into those caches. And that's 100% dictated by the memory bandwidth. And so one thing I always encourage teams that I work with, customers that like I advise, companies I advise, is nail that layer down. You have to do tricks. You have to overlap and keep the compute busy while you're loading data in. I mean, these are relatively well-known concepts these days. It's just taking it from concept down to the hardware level. There's a lot of layers in between that are not well documented, and that's what my book focuses on. Yep.
Really cool. I feel like to probably make the most of performance engineering for AI systems, you probably would. I mean, it would be tough in a podcast episode like this in an hour to convey to people all the things that they need to know, or, even the key things that they need to know. Because I imagine a lot of it is specific to the circumstances that they're in. Would you say that's correct?
Right. At the end of the day, everything is workload dependent. You're typically fixed in the hardware that you can get, the budget that you have, right? This was uh, in like particular DeepSeek, didn't even have the same GPUs that the Western labs have. And so trying to, and I was just looking at the book here. Yeah, after, like, you write 1,000 pages, you can't even like really remember where anything is. So the secret to this book, by the way, real quick, is that this is actually 3 different books. And multiple times I said there was only going to be 1 or 2 chapters on CUDA. Now there's, I think, 8 chapters on CUDA. And the reason is I couldn't find any single resource. Like, there's a lot of CUDA books out there, but they're written by people for specific use cases like fluid dynamics and things that just aren't really relevant to the LLM world. There's certainly overlap in the underlying concepts, but being able to tie, here's a model, here's a DeepSeek model, or here's GPT OSS by which is the open source version out of OpenAI. How do I map that in a mechanical, sympathetic manner? So this is one term that I've loved for years and years since my old Java days, trying to optimize JVMs and things, is this concept of mechanical sympathy. And this is also ties into a piece of advice that I always give to my friends, and specifically my friends' children, is if you're in a CS program right now and thinking that your skills are not going to be relevant, really dive deep into the hardware and try to understand your surroundings. Now, the hardware is going to change, of course, by the time they graduate and stuff, but at least, like, don't stop at the software layer. Think of this hardware software co-design. The algorithms haven't changed that much. There's been tweaks over the last few years, different layer normalizers and like different parts of the transformer. But what is sure to change is the hardware is going to get faster, the memory bandwidth's going to change, and you really need to be able to think in terms of that whole stack. And that's why this book exploded into 1,000 pages. It was because every layer that I would uncover, I'm like, oh man, this is going to be way better if I can explain how all this works together.
Right. So one of the sub books in your 1,000-page book, AI Systems Performance Engineering, is CUDA. What are the other 2?
Right. So think of it like, so there's, I think, 3 or 4 chapters on PyTorch. So, like, think of it like the three parts of the co-design are the hardware, the software, and then like the algorithms. And so really the first few chapters kind of set up the hardware, set up the operating system, because all these things matter. One small change at the operating system can make or break and cost you millions of dollars, right? And so I've got a whole chapter dedicated to that, and basically all of those different layers. So hardware, software. On the software side, there's basically a whole book that's in here. The last I think 6 or 7 chapters that are on like inference. I do cover training. However, I decided to really, really dive deeper into inference because of where everything's at with the current. I'm trying to keep this book relevant for the next couple of years, and so it's inference, hardware.
And inference is where, you can correct me if I'm wrong on this, but I believe when you think about what the workloads that a given GPU is handling in its lifetime, 99% of that is going to be handling inference, not training.
Absolutely. Yeah. Even for, post training, for the reinforcement learning, huge, portion of that is actually doing like the inference part of it, and then just a little bit of weight adjustments and absolutely.
Yeah, and so that this co-optimization that you've been talking about of hardware, software, and algorithms, those three pieces together, it's a concept that you refer to in your book as mechanical sympathy. Uh, yeah, so I don't know if there's anything more to say about that term.
Yeah, it's a term. Martin Thompson, a famous, computer scientist, software engineer, many years ago, um, described it. He was making this analogy to Jackie Stewart, who is a British Formula One champion, and Jackie Stewart was famous for not just being a driver, but also able to construct and build the cars. And that was really something very unique to things back then. And yeah, I would say yes, even today, I don't think a lot of drivers are really capable of like turning the wrench, right, and making these adjustments. They can give the feedback, which is what the constructors need to make changes and right, like throughout the race and things, but they're not necessarily the ones that are able. So, and it's a huge advantage when you're able. So, a really big sort of emphasis, and this comes through with the GitHub repo for this book, by the way, which has about 700 examples, and I think is about to reach maybe 800 by like this weekend. I'm constantly updating the GitHub repo, which is documented in the book. But something I very much emphasize that I don't see teams doing is paying attention to the GPU metrics. And this is more than just temperature, which can certainly affect things, and more so than CPUs. But look at the low-level counters. It's something NVIDIA has tools, but they're very cryptic. They're command line tools. They've got a UI, but it's janky and it's outdated. And I know that they're working on something better. But actually, one of the startups that I advise called Zimtrace, they've sort of cracked this, and they're sort of like, if you're familiar with like App Dynamics, they are sort of the runtime, the kind of modern version of like App Dynamics, where it can look at the CPU, the GPU, it can look at PyTorch, give you exact stack traces. This is exactly what I was about to build, by the way, after writing this book, was like realizing, because part of me writing a book is figuring out like what are the boundaries of this space, and can I find people that can fill in these things. And so it's a very untapped market, and being able to in real time make adjustments, turn the wrench, right. And so yeah, profiling down to that level is extremely important, and not just stopping at the PyTorch profiler, which is what all the PyTorch community. It's so funny because it's just one or two more commands away, but the PyTorch folks seem to just stop at the PyTorch profiler. But that is not enough to really dive in and make these changes.
To give our listeners who aren't aware, who maybe aren't hands-on practitioners of AI, PyTorch is by far the most popular library today for putting the pieces together of an AI system. And what's the PyTorch profiler? What do you see in that, and why isn't it enough?
Yeah, PyTorch profiler. The reason the PyTorch community likes it is because it's Python friendly. It's using terms that are familiar to PyTorch users. It's showing you where time is being spent in your training job or in your inference, or basically any PyTorch job that you're running, code base that you're running. But it really only gives you a few different aspects of it's the tip of the like iceberg when it comes to trying to actually really understand the system and really achieve mechanical understanding of the whole system. So and it'll show you sort of high level that the CPU is being used here, and that the GPU now comes in, and there could be better overlap here where you could be moving data at the same time. But there's like probably 50 to 60 more critical, or just as critical, metrics that are needed to really move things forward. And so that's why I haven't really seen a whole lot of like progress in terms of performance, or that like that type of progress is really limited to the frontier labs or folks like DeepSeek that are, taking the time to really understand what's beneath the covers.
What are the kind of, you mentioned there kind of a dozen or so metrics that are critical, that are difficult to see? What are kind of like the key ones that we might not be aware of, and how could we possibly see them?
Sure. Yeah, the GPU does expose a lot of counters, and there's really the two or three main tools are at the kernel level. So kernel is like what it's the program that the GPU actually runs, right? And when you program to a GPU, you have to realize that part of it's happening on the CPU to kind of prepare the data. Then the data has to ship over to the GPU, and now the GPU has a whole bunch of constructs and hardware optimizations that have been built up for the last 10 years specific to AI. So there's things like the streaming multiprocessor, right? That, think of it like a core or a set of cores that, you would tune for like parallelism on the CPU. Well, the GPU has that same thing called, streaming multiprocessors. There's the amount of time being spent on those streaming multiprocessors. There's a percentage that's called the occupancy. And it's basically all about the like utilization of the hardware. But the other really key critical thing is that there's separate pipelines. There's instruction pipelines that power all of these different portions of the GPU. So the GPU has specialized chips for softmax, which is used super heavily in like transformer world. And so what we've seen is since transformers, 2016, 2017, once NVIDIA like found out that this is what researchers are using, they started building in these specialized function units there, which short like yeah, so that acronym is then SFU for specialized function unit, to handle those transformer specific operations. And then of course there's also tensor cores, which are specialized cores that can do floating point 8, floating point 16. So like specialized operations that of course are common in transformers. Those all have separate pipelines. Trying to move memory in and out, like that's another pipeline. And so you really have to understand, how can I best like parallelize all of these things and make sure that they're all fully utilized all at once.